Okay, so in this video we're going to go through the basics of limits and find the limits of functions. So when you're about ready to consider a given function like this one here, f of x, they're going to start you off with two different kinds of situations here. In one case, they'd like you to first figure out what f of 2 is going to be, or f of a, whatever given value that they want here. The second thing they're going to ask you to do here is figure out what the limit is as x approaches that same number. I like to call that 2 right there in that limit there the point of attack. So right at the point of attack there at 2, what's that function going to look like? So let's just look at the first part. Let's figure out what f of 2 is. Pretty simple. Just take yourself out to 2 on the x-axis, and what they want you to look for when you go out to 2 is just what's the y value that goes with it. So making our way out here to the next y value here, to the y value, as we go to 2, notice we travel up to that point right there in the function, which gives us a y value there of 6. So at the point on the graph where the x-coordinate is 2, the y-coordinate is 6, so to answer that question, just simply say that the f of 2 is equal to 6. So next what they want you to do is figure out what the limit is as f of x approaches, as x approaches 2. So picture this here. If you see 2 right down there on the function, what they want you to be able to do is imagine yourself getting closer and closer and closer to 2, but never actually becoming 2. If you were to do that, notice what the y values actually do here is those y values get closer and closer and closer to 6 as well, just like we did before. So when we look at those points in the graph that are not equal to 2 but get really, really close to 2, the y values approach and get close to 6. So what we say there is the limit of f of x as x approaches 2, is we say that 6. The reason why both of these two values here both give us answers of 6 is the fact that right here at this point, when this graph kind of does its thing, it's continuous right there at that point. There's no breaks in the graph. So in some cases like these, where the graph's continuous, the limit and the evaluation of the function at that given point are going to be one and the same. So now if we take a look at this problem with these two cases here, f of 4 and the limit of f of x as x approaches 4, notice something different happens. As we try and figure out what f of 4 is at exactly 4, notice that something happens on that graph there. We have a hole in the graph. So as we approach the function from here, we'll have that hole in the graph to contest with. So we run across a little bit of a problem here. And that problem that we end up running into is that the function's undefined at that spot. Let's look at the limit though. If we go to the limit as f of x of x as x approaches 4, something different happens here from the previous problem. Notice as we start to squeeze in on 4, the y's actually can squeeze in on a value as well. And notice that that value that we're actually squeezing in on would be about right there, and that value is 3. So what we can say here is that our limit here as x approaches 4 of f of x is indeed 3. So notice in this case, because we're never actually truly on 4, we can actually make an answer here, and we can actually state what the limit is. The limit as f of x as x approaches 4 would be 3. So one important concept about limits is that if the function is continuous at that given point of attack of a, then we can find the limit by just simply figuring out what f of a is. What we mean by that is if you look at example a here, the limit as x approaches 3 of x cubed minus 5x squared plus 7x minus 10. If you investigate that function right at the point of attack at 3, notice that the function is actually continuous right at when x equals 3. Which means that we could find an answer for this limit if we just simply plug in 3 in for x throughout the function. So in other words, to find this limit when it's continuous there, just replace all of the x's with 3's, and then just simply evaluate what that solution is going to be. And once you've evaluated that solution there, there's your final answer there. So the limit as x approaches infinity, not infinity, but approaches 3, is now we can simply say that the limit here is -7. Same can be true for this next problem over here. Investigate the function first. Notice that the function is indeed continuous at when x equals pi, so we can find an answer here. So then to evaluate the limit here, just simply replace the x's that you see there with pi. So substitute pi in there and pi in there. Where is that coming from? Because our point of attack is right there at pi. Next, simplify that. Now the cosine of pi, using our unit circle knowledge, tells us that the cosine of pi is nothing more than -1, so we can replace it right there. And so there it is. There's our limit. Our limit here is -1 over pi. Now, there are going to be some snags to finding limits. It isn't always as easy as just substituting the number in here. Notice that if you were to look at the point of attack here at 3 and substitute that 3 in there, in the numerator and the denominator, you're going to run into a big problem here in the denominator, right? It's going to make that whole denominator there a 0. What that's trying to tell you here is that unfortunately this function is discontinuous at that given value of x equals 3. If you were to look at this graphically, this is what it would end up looking like here. You'd have your function, and then right here at 3, traveling right up there, you see that we're going to have a hole in the graph right there. Now, having the graph here available can kind of give you a suggestion as to one possible approach to actually figuring out what the limit is now that you have a graph here, you can see and make a nice guess as to what those values are approaching here and make a pretty good accurate reading on it. So 6. Let's show you how this works algebraically. The move that you're going to have to make here is looking at both the numerator and denominator is look to factor it. X squared minus 9 can get factored as a difference of 2 squares, as x plus 3 and x minus 3. And then what we can do here is this x minus 3 here can cancel with that x minus 3 there, leaving us with just simply the x plus 3 left over. Now we can find that limit much the same way that we did in the previous problems by just simply looking at the point of attack of 3 and just plugging that 3 into the function. So now we're just going to take simply 3 plus 3. And that gives us the 6 that we had originally found by just looking at the graph. So further problems get handled in the same manner. One thing that you do want to just establish here to justify your canceling and your factoring is notice that at the point of attack, when you put that 4 in there and that 4 in there, you'll end up with 0 down there. So it does require us to do a little bit of factoring here. And so in this particular factor job, when you look at the numerator there, you've got to find two numbers that multiply together to give you -8, and the same two numbers need to add to give you -2. So in this situation, it's got to be a +2 and a -4. Down below, we can factor out the x here because we have a GCF of x, so factor that out, and what's left over is x minus 4. Good news here is that we can cancel out the x minus 4's, leaving us with x plus 2 over x. Now we can just simply substitute the 4 in for both those x's. So just like that, and now we can take 4 plus 2 and divide it by 4, reduce the fraction, and we're staring at 3/2. Over on this other problem here, a good first move, noticing that it's undefined at the point of attack there at 0, is let's just divide every one of those 3 terms in the numerator, divide them by h. So there we go, dividing each one of those 3 terms by h just drops everything down a power. Notice the h's will cancel out on the back end there, just leaving you with -6. Now, because it's defined here, now we can just substitute 0 in there, which really just eliminates all of our h's out of the pictures, leaving us with that -6 that didn't have an h to pair up with. Okay, so there we go. Alright, so occasionally you are going to be throwing some real, tough ones. The purpose of me showing you these two problems is in those situations where at the point of attack it's undefined, so you can see that for both of these here. Plug in a 0 for A, example A there, you're going to get a denominator of 0. Plug in a 1 in example B, you're going to get a denominator of 0. But also notice that factoring is really no-go here either. So when both of those two cases kind of fall through, what you should be doing next is just try a number that's really, really close to 0. So if factoring is no good, try a number that's close to 0, so that way you can get maybe a good idea and make a good educated guess as to where the limit's going. So kind of how I see this going here is if you try and pick a number that's really, really close to 0, for example A right there, maybe you might have thought that maybe trying 1 would be an option. So you try 1, thinking 1's pretty close to 0, so you substitute there, 1 minus the cosine of 1 divided by 1 squared. Realize you're going to get a decimal there of 0.45, it's 5970. Great. But couldn't we try a little bit better? Couldn't we do better than that? So when I'm talking about trying numbers that are close to 0, really get nuts with it. A number that could really get really close to 0, you could try 1/10. Notice what happened to the decimal. Get even crazier with it. And as we keep on getting crazier and crazier with that number, that decimal starts to get closer and closer and closer to 1/2. And so there it is. We can now make a pretty educated guess to say that the limit as x approaches 0 there would be 0.5. Notice that we approached this as 1 and we started to shrink it and get it closer to 0 coming from the top. We could have done the same thing coming from the bottom there and getting closer and closer and closer to 0 that way. So it doesn't really matter which way you approach it. Just pick a number that's really, really close to 0. We can do the same thing over here with this problem. In this situation, don't try a number that's close to 0. Actually, we want to try a point that's close to the point of attack of 1. So we need a number that's really, really close to 1. So notice in these situations, it doesn't matter which one you use here. Notice just in this little row right down here that as we are trying numbers that are close to 0, either it being 0.999 or 1.001, we got two numbers here, 1.0005 or 0.99950. Both those cases, the number is close to 1, isn't it? And so that's the final conclusion that we can make here, is that the limit of this particular function is 1. So try not to use you don't have to necessarily use it when you run across problems you can't factor. Even if you're running across problems that you are having trouble factoring, if your factoring skills are a little rusty, you can still do this trick. Plug in a number that's close to the point of attack and just compute it and figure it out. And you can get a pretty good estimate as to what the limit's going to be.